It's my pleasure to introduce Wolfgang Altmannshofer. He's an associate professor at the University of California, Santa Cruz. He's also a member of SCIP. That's the Santa Cruz Institute for Particle Physics down there. He got his PhD in 2010 from Technical University of Munich. And he's done postdocs at Fermilab and also Perimeter Institute in Canada. And he had a faculty stint at the University of Cincinnati, and I just learned has been 5 years now at UCSC. So we're excited to hear this talk on particle physics, and thank you so much for joining us. And we'll be hanging on your every word. And I hope you have time for questions because we probably have many.
All right. Yeah, thanks a lot for the introduction. Thanks a lot for the invitation. It's a great pleasure to give this talk on particle physics. I will try in this colloquium to give an overview of what particle physics is about, what are the sort of most exciting research directions at the moment, and also how particle physics might look in the future. I want to frame this discussion in the context of what is known as the P5 report. So P5 stands for Particle Physics Project Prioritization Panel. So that's a panel of physicists that convenes every 10 years or so, and sort of comes up with a vision of how particle physics should look like in the coming decade and beyond, and also makes recommendations to funding agencies of which type of research in particle physics should be funded. And the most recent of these reports came out just a month ago. So in December 2023, there was the latest P5 report. And they came out with this graphics that I'm showing here in this slide, and which sort of summarizes the various research directions in particle physics. And I want to spend a couple of minutes just discussing this graphics here, and then unpack various things throughout this colloquium. So what they did is they organized the various research directions in those 3 panels that you see here. And let's start with the right-hand side, this panel that's called Illuminate the Hidden Universe. And this comes with 2 themes. The first one is determine the nature of dark matter. I'm sure you've all heard of dark matter. We have overwhelming evidence from astronomical and cosmological observations that there is something like a dark matter in the universe, starting from rotation curves of galaxies to the evolution of the universe as a whole. We know that there's a big chunk of stuff that is out there in the universe is in the form of dark matter. And so particle physicists try to understand what the dark matter is. It's very plausible that the dark matter is some form of particle, or maybe it's conceivable that it's even more than one particle. There's a whole dark sector of particles that comprise the dark matter. And yeah, particle physicists try to understand which type of particles that could be, how what their properties are, how do they interact with each other, and also how do these particles interact with us, how do they interact with particles that we are made from, how can we detect dark matter in experiments, maybe can we even produce dark matter in the laboratory. These are all questions where particle physicists are working on. The second theme in this panel is shown here as understand what drives cosmic evolution, and that has to do with the expansion of the universe as we observe it now. We seem to be in an area of accelerated expansion, and what is usually that is then referred to as an area where dark energy is the biggest component in the energy budget of the universe. Dark energy is much less understood or well defined in terms of what its relations are to particle physics. Is it some particle, some field that is relevant in the context of dark energy that is driving the evolution of the universe? But because it's a complicated question and it's not really clear how particle physics enters in that question, it's something that is the mind of many particle physicists trying to understand these type of questions. Then let's jump over to the left-hand side of this chart here. There's a panel called Decipher the Quantum Realm. So that is now dealing with known particles and trying to understand their properties. And the two types of particles that are singled out here are neutrinos and the Higgs boson. Higgs boson was discovered now more than 10 years ago at the LHC. So it's the last missing ingredient of the standard model of particle physics. And we still have many questions about the Higgs boson. After its discovery, the goal is now to determine its properties as precisely as possible and to test if its properties are as predicted by the standard model of particle physics or if there are any deviations. So a lot of work is going into revealing the secrets of the Higgs boson, so trying to understand the Higgs boson, trying to understand if it behaves as predicted, and with the hope that it might show different properties which would point beyond the standard model. And then the second thing, they elucidate the mysteries of neutrinos. Neutrinos, of course, have been known for a long time. Neutrinos are very elusive. They're very hard to detect. So studying neutrinos precisely is difficult. It requires a huge effort to detect neutrinos and to get precision measurements of their properties. And there are still things that we don't know about neutrinos. So a lot of effort also is going into understanding neutrinos better and trying to understand if they behave as, again, predicted in the standard model, or if there are features of neutrinos that point beyond the standard model. So that's a sort of a second research direction in particle physics, trying to understand particles that we know of with as good precision as possible. And then the third panel here in the middle, sort of a more open-ended research direction, is just about exploring new things, exploring new paradigms in physics. We have many good reasons to think that there is physics beyond the standard model. I mean, of course, here on the one hand, we have things like dark matter, but beyond dark matter, there are other good reasons to believe that there is more stuff out there that we haven't seen yet, new particles, new interactions. And then the question is, what are the best ways to explore those things, or what are the best ways to detect maybe new particles and new interactions? And there are, roughly speaking, two approaches to that. The one is a search for direct evidence for new particles. So that is what one does at particle colliders, when it's colliding particles with higher and higher energies, with the hope of producing new things, new particles, and try to then study and understand them with as high precision as possible. And then the second avenue would be pursue quantum imprints for new phenomena. So that refers to, again, precision measurements, making precision measurements of processes that we know exist in the standard model. And by comparing experimental results with standard model predictions, one tries to find out if there's consistency, or if there's no consistency, then this would point indirectly to some form of new physics that should be out there, that one then might be able to target in collider searches directly. That's sort of a very quick and broad overview of the current research directions in particle physics. And yeah, throughout this colloquium, we will go into a few of those aspects in more details. But before doing that, let me just back up a bit and talk a bit about sort of the basic motivation of particle physics. And the basic motivation is, well, it's curiosity. We try to understand what are the most fundamental constituents of nature and how do they interact with each other. The questions that we ask are very simple questions, but very deep questions. We try to understand what is the world made of, and what holds it together. And over the past century or so, there's been a really remarkable progress in answering those questions, addressing those questions, and it culminated in the development of what is known as the standard model of particle physics, which does exactly that. It describes the basic constituents of matter as we know them, and their interactions. And what is shown in this chart here is the particle content of the standard model of particle physics. So these are the particles that we know exist, that we can produce in the laboratory, that we can study with high precision. So these particles are organized in a particular way here in this outer ring. Is what I would call metaparticles. So these are spin 1/2 fermions, and they come in different types. There are 3 up-type quarks, the up quark, the charm quark, and the top quark. There are 3 down-type quarks, the down quark, the strange quark, and the bottom quark. Then there are 3 charged leptons, the electron, the muon, and the tau, and 3 neutrinos. And all those together are the meta content of the standard model of particle physics. So again, these are spin 1/2 fermions. They're fermions, that means they obey the Pauli exclusion principle, so you can't stack them all on top of each other. So if you put many of them together, they form macroscopic structures. So that's what matter is. And then the remaining particles shown here in this chart are in the second ring here. These are force carriers, the particles that mediate interactions between the metaparticles. We have the photon, which mediates the electromagnetic interactions. We have the gluons, which mediates the so-called strong force between quarks. And we have the W and the Z boson, the weak gauge bosons, and they mediate the weak interactions between the fermions. And then in the center of this chart, we have the Higgs boson. The Higgs is special. It's the only spin 0 particle, the only fundamental spin 0 particle that we know of. And yeah, as I said, it was discovered more than 10 years ago now at the LHC. And that is the particle which provides mass to all the massive particles in the standard model. Without the Higgs, all the particles would be massless, which is not what we observe. We observe that most of those particles have masses, and in the context of the standard model, those masses originate from the Higgs boson. I took this chart from, this chart is shown in a movie called Particle Fever. It's a movie about the discovery of the Higgs boson. If you haven't seen this movie, I can highly recommend it. It's a very good movie. So feel free to check this out at some point. So let me talk a bit more about the Higgs boson. It plays a central role in the context of the standard model. And I mentioned several times already, it was discovered more than 10 years ago in 2012. And here's one of the plots that shows the discovery of the Higgs boson. What is shown here are event numbers. It's a histogram of events that have been detected at the LHC, at the Large Hadron Collider at CERN in Switzerland. And these events are binned in a quantity called M4L. So that means one is looking at events where 4 charged leptons were produced. Typically either an electron-positron pair and a muon-antimuon pair, or 4 muons, 4 electrons. And what is shown in this chart in purple and red is the expectation from the standard model without the Higgs boson. So if there is no Higgs boson, you would expect that the distribution of events should follow this red curve. And you see that the various data points, they are indeed scattered around this red curve for most of the plot. Apart from this region here around 125 GeV, there one sees a clear excess of events, an additional bump in that spectrum, and that is the effect of the Higgs boson. So there's an additional resonance that decays into 4 leptons, and that resonance is the Higgs boson. It has a mass of around 125 GeV, and it can have a decay into 4 leptons, producing this excess of events. And this discovery of the Higgs boson. Oh, I hear some. Is there a question?
I don't think so. We are paying close attention, however.
Oh, sorry, I heard some background noise. I'm sorry about that.
I think it's just echo from the room.
Okay. Yes. But yeah, feel free to interrupt me anytime. So I'm happy to take questions also during the colloquium. Anyway, yeah. So this plot and several others of that type, they showed conclusively that there is this Higgs boson, and this led to the Nobel Prize in 2013 for Englert and Higgs, who predicted the existence of the Higgs in the 1960s, and yeah, so this prediction of the Higgs boson was confirmed in 2012 at the LHC by the ATLAS and CMS collaborations, who saw those additional peaks, these additional bumps in those spectra, either of 4 leptons or also other ones, like, for example, the 2-photon channel. By now, many Higgs bosons have been produced at the LHC. Around 10 million of them have been produced. The Higgs bosons themselves, they are not stable. They decay very quickly in around 10 to minus 22 seconds. They decay into other particles, for example, into 4 leptons or other things. And the standard model predicts very precisely how the Higgs is produced and how it again decays. So here are a couple of Feynman diagrams that show examples of how the Higgs gets produced and how it decays. So it can start out with gluon, then you produce a Higgs. So you start with quarks, then you produce Higgs in association with quarks. So you produce a Higgs in association with W and Z bosons, etc., etc. And here you have several decay modes of the Higgs into a W and a Z, or 2 photons, or a bottom quark, or a charm quark, or a tau, or a muon. So there are many ways the Higgs can be produced and can decay into. And as I said, the standard model makes very precise predictions about the various rates and probabilities that those things happen. And then one can, now with this huge statistics that one has at the LHC, with this 10 million Higgs bosons, one can precisely measure the various types of Higgs production and decay, and compare to the standard model predictions. And here's a set of plots that show this. So here are various types of production processes of the Higgs and various decay modes of the Higgs, and these plots compare the standard model predictions, which are these red lines, with the measured values, which are the black dots with the corresponding error bars. And across the board, one sees a very good agreement between the standard model predictions and the measurements. And in many cases, one has a very high precision, both in the standard model prediction and in the measurement by now. Sort of 10% precision in the measurements, and good agreement with standard model predictions. So that's a set of plots that I took from a paper by the ATLAS collaboration, which came out for the 10-year anniversary of the Higgs discovery. There's a paper called A Detailed Map of Higgs Boson Interactions by the ATLAS Experiment 10 years after the discovery. And one can also then translate those type of plots into actual couplings of the Higgs boson to standard model particles. So that is shown in this plot here by a similar paper by the CMS collaboration, a portrait of the Higgs boson by the CMS experiment 10 years after discovery. So again, sort of a 10-year anniversary paper where the collaboration at the LHC combine all the information that they have about the Higgs boson so far. And so what is shown in this plot is again, a standard model prediction of how the coupling of the Higgs boson is related to the mass of a corresponding particle. And because the Higgs provides mass to all the standard model particles, the coupling of the Higgs to the standard model particles is proportional to the mass of those particles. So the standard model predicts that all those couplings should lie along that diagonal line here. And then indeed the measurements that you see here, coupling to muons, to taus, to bottom quarks, the W, the Z, the top quark, they indeed all lie perfectly on that line, again confirming that the properties of the Higgs boson that have been tested so far agree very well with the standard model predictions. Still, there are many open questions about the Higgs boson. We don't know yet if the Higgs actually gives mass to all the standard model fermions. We only have tested that for the heaviest of the fermions, because there the coupling of the Higgs is largest. That's sort of the easiest things to test. But for very light standard model particles, the electron, for example, or the up quark, the down quark, which are the lightest charged fermions, we actually don't know if the Higgs boson gives mass to those particles. The coupling is so small, the mass is so small that it's very difficult to directly test that, for example, at the LHC. But it's something that we would like to understand better in the future. And there are many other questions that we have about the Higgs. Is Higgs related to baryogenesis, to the fact that there's more matter than antimatter in the the universe. It's a question: are there more than one Higgs boson? It could very well be that the Higgs is not alone by itself, but there are several Higgs bosons. Maybe some of Higgs bosons, maybe there are additional Higgs bosons which give mass to the lightest fermions. Maybe there are different Higgses which provide masses for different particles. That could be the case. Is the Higgs boson related to dark matter? Is it related to dark energy? We don't know this. There's a question about the Higgs vacuum. Is it stable? It could be, or it's very likely, if we look at the parameters of the standard model, that our vacuum is actually only metastable, and that there's a non-zero probability that we could tunnel into another minimum. So these are questions that one can try to address. And then one thing we will come back to later is there something that stabilizes the Higgs mass against quantum corrections? So we have measured the Higgs mass. It's around 125 GeV. That sets the scale of the particles in the standard model. But from theoretical considerations, it would be much more natural if the Higgs was as heavy as the Planck scale, if it was many, many orders of magnitude heavier. So the question is, why is the Higgs so light? Why are all the other standard model particles so light compared to the scale of quantum gravity? And yes, that we will come back to that question soon. For the moment, I want to talk a bit more about other particles of the standard model that we know of and their properties. So in particular, I want to talk about the quarks and the leptons, the matter content of the standard model. That the Higgs provides mass to those particles. So which masses do those particles have? Here's a chart of those masses. So this graph shows the mass of the top quarks, the charm quark, the up quark, the 3 down type quarks, the bottom strange and the down, and the 3 charged leptons, the tau, the muon, and the electron. And one curious thing is that those masses, they span many orders of magnitude, more than 5 orders of magnitude between the top mass, the heaviest fermion that we know of, and the electron, the lightest charged fermion that we know of. Seems to be some weird hierarchical structure in those masses. And we don't know what the origin of those hierarchical structures are. The standard model can accommodate those masses. It corresponds to how strongly the Higgs couples to each of those particles. But there's nothing which sort of would explain why the Higgs couples very strongly to the top, but doesn't couple very strongly to the electron, for example. Why is there this huge hierarchy in masses? We don't know that. Situation gets maybe even more stranger if we include neutrinos in this picture. We don't know exactly how heavy the neutrinos are. They are large error bars on those masses, but we know that they are many orders of magnitude lighter than all the other particles. There are some explanations of why that might be the case, and it has to do with the fact that neutrinos could be their own antiparticles. But again, it's not known why neutrinos are so much lighter than all the remaining particles in the standard model. Given that there's such a hierarchy between the masses of those particles, what one finds is that the heavier ones, they are not stable. So heavier particles, heavier fermions in the standard model, they decay into lighter ones. And there's a particular pattern of decays that happens in the standard model. So for example, up type quarks, they can't decay into each other. So the top quark can't decay into a charm quark or an up quark. Those transitions are forbidden. In the same way, there are no transitions within the down type quarks. The bottom quark cannot decay directly into a strange quark or a down quark. One says there are no flavor changing neutral currents in the standard model at tree level. Those things are forbidden, and it's just baked into the structure of the standard model. So the mathematical description of the standard model, the rules of the standard model, they don't allow for these types of transitions. What is allowed are transitions between the different generations of quarks by going from up type quarks to down type quarks, or going from down type quarks to up type quarks. And those transitions are mediated by the W bosons of the weak interactions. And the relative strength of those transitions is parameterized by a 3x3 matrix, the so-called Gabibo-Kobayashi-Mascava matrix. So we have these 9 entries in this so-called CKM matrix. So if we pick out on one element, VUB, for example. VUB tells us what is the relative probability that a B quark decays into an up quark, and the VCB would correspond to the probability that the B quark decays into a down quark, for example. So we have these transitions between the up-type quarks and the down-type quarks, and the relative strength of these transitions is parameterized by this CKM matrix. In the standard model, the CKM matrix is the only source of flavor violation. So flavor, I should have mentioned that flavor refers to this three generations of quarks that we have. So we say we have three flavors of up-type quarks, three flavors of down-type quarks. And the only way to change flavor, to change between those different types of quarks, is to go through the CKM matrix. One can show that the CKM matrix can be parameterized by four parameters, but one can measure many of those transitions and then over-constrain those four parameters and check if everything is consistent and everything follows this picture of the CKM matrix and everything follows those transitions as predicted in the standard model. And those tests were carried out at the so-called B factories, Babar and Bell. These were experiments running from around 2010. And what those experiments did is they were colliding electrons and positrons and producing pairs of B mesons. B mesons are bound states of a B quark and some light quark. And those B factories produced billions of those pairs of B mesons and very precisely studied the decays and other properties of those B mesons. And in that way, got access to many of those parameters of the CKM matrix and over-constrained those parameters. And then the result of that is often shown in this picture of the so-called rho bar eta bar plane. The rho bar and eta bar are two of the four parameters of the CKM matrix. And the various colored regions that you see on this plot are the constraints that one obtains from measurements at the B factories of those parameters, rho bar and eta bar. And if everything is consistent, all those different colored regions should overlap in a single region, and that's exactly what happened. This region here, that is the region, the overlap of everything that have been measured, and everything consistently goes through that region. And this overall consistency of the CKM picture of flavor violation that led to the Nobel Prize in 2008 for Kobayashi and Maskawa. And these tests of the CKM picture, they continue. So there's a follow-up experiment to the Bell experiment called Bell 2, which is running at the moment. And this is the situation right now of this rho bar eta bar plane. So what is shown before, this was in 2008, the situation in 2008. By now, summer 2023, so this is the situation. And we have now much more precise measurements of all those various quantities that enter in those measurements of rho bar and eta bar. And again, very nice consistency among them all. It's a level of 10% or better. So we have a very precise confirmation of the CKM picture of flavor violation. If we look at the corresponding entries in the CKM matrix, the measured values of those CKM matrix elements, but again find some weird hierarchical structure. So some of them are very close to 1. Others are smaller by a factor of 5 or so. Others are smaller by yet another factor of 5. And then a couple of them are very small, smaller than 10 to the minus 2, or maybe a few times 10 to the minus 3. So it's again the hierarchy that's showing up in this flavor transitions of the quarks. And again, we don't know why there is such a hierarchical structure. There's no reason a priori why there should be a hierarchical structure. It could be all just roughly order 1 numbers that show up in this matrix, but it turns out to be a hierarchical pattern of entries that one finds in the context of these flavor changing transitions. I can look at something analogous in the lepton sector. So if you look at transitions between charged leptons and neutrinos, again, we don't have any flavor changing currents in the standard model. There are no transitions, let's say, from a tau to a muon or from the tau to an electron. But there are transitions between the different flavors of charged leptons and the different flavors of neutrinos. And the analog of the CKM matrix is called the Pontecorvo-Maki-Nakagawa-Sakata matrix, the PMNS matrix. And again, it parameterizes the relative strengths of the transitions between the three flavors of charged leptons and the three flavors of neutrinos. And again, one can ask, what are the entries of that PMNS matrix? And here one finds that all of those are more or less of the same order. They all lie within one order of magnitude. It doesn't seem to be a hierarchical structure in the PMNS matrix. So the mixing of the charged leptons and neutrinos seems to be very different than the mixing between the up-type and down-type quarks. And again, we don't know why that is the case either. So there are many questions that we have about those quarks and leptons, even though we know many of their properties, even though the standard model describes their properties very accurately. Everything seems to be consistently described in the standard model. There are many why questions that we don't know the answer of. The zeroth order question would even be, why are there three flavors of quarks and leptons? Why are there these three copies of up-type quarks, down-type quarks, charged leptons, and neutrinos? We don't know that. What is the origin of the hierarchical spectrum of the fermions? What is the origin of the hierarchies in the quark mixing? And why is lepton mixing so different? Why it doesn't seem to be there to be any hierarchy in lepton mixing? And that's the set of questions is sometimes referred to as the standard model flavor puzzle, a set of open questions about flavor that we don't have answers to. But there are many more questions that the standard model doesn't answer. And we mentioned several of them already earlier, and I'm sure you have seen lists like that. So we have the question about what is dark matter, the question what is dark energy, where does the matter-antimatter symmetry in the universe come from? Is there something like grand unification, where all the various interactions get unified into a single interaction? What is the solution to the so-called strong CP problem? What is the solution to the so-called hierarchy problem? These are all open questions in particle physics. And I want to spend a bit of time discussing the hierarchy problem in more detail. So the hierarchy problem is related to the question of what gives mass to the Higgs itself. The Higgs gives mass to all the other particles in the standard model. What gives mass to the Higgs itself? Well, the answer is there's no symmetry or no mechanism that is forbidding a mass of the Higgs boson. You can just have a mass by itself. The Higgs in this sense is different from all the other particles of the standard model. All the other particles of the standard model by default would be massless. Their mass terms are forbidden, and they only can be introduced by introducing the Higgs. But the Higgs itself, it just can have a mass. So we can just add a Higgs mass to the Lagrangian of the standard model by hand. That's not a problem to do that. But on the other hand, that also means that the Higgs mass is not protected from any quantum correction. So if you try to theoretically compute what are quantum corrections to the mass of the Higgs, one actually finds that they are very large. If one naively estimates them, these quantum corrections to the Higgs mass should be of the order of the Planck mass, the scale of quantum gravity. And if you look at the numbers, these quantum corrections are many, many orders of magnitude larger than the known measured value of the mass of the Higgs boson. In principle, that's fine. There's no inconsistency about that. One can always adjust that bare mass such that there is a cancellation between the bare mass and these quantum corrections, that you end up with the known value of the Higgs mass around 125 GeV squared. But it looks very weird. It looks very weird that you have these very large quantum corrections and you have to add a bare mass term to it, and you have a huge cancellation to end up with a small number. But again, there's nothing inconsistent about that. It can happen that you start out with two big numbers, you add them up or you subtract them from each other, and you get a small number. So you can just, now here's an example of that. So if you look up the surface area of Canada and the surface area of the United States, they turn out to be almost identical. So if you subtract them from each other, you get a very much smaller number than the individual surface areas by themselves. And there's nothing inconsistent about that. There's no reason why the surface area of Canada should be the same or approximately the same as the surface area of the United States, but it just happens to be so. There's sort of a percent level tuning of those numbers that you end up with only a percent once you subtract those two numbers. So there's nothing inconsistent about this in principle. The problem is that in the context of the Higgs mass, the fact that these quantum corrections are so huge that you need an enormous amount of tuning to get to the observed mass. And if you translate this into this picture of these surface areas here, the tuning that you need in the Higgs mass in order to get the observed value corresponds to the difference in the surface areas of Canada and the United States to be roughly the size of an atom. And that's pretty crazy. So in order to avoid such type of fine-tuning, in order to avoid these large quantum corrections to the Higgs mass, we do expect that there's some physics that reduces these quantum corrections to a manageable level. So we do expect that there is some new physics that would protect the Higgs mass from quantum corrections. And this new physics should be not much heavier than the Higgs itself. It should be around the TeV scale, or not much heavier than that. There are many options of what that new physics could be. We don't know exactly what that new physics is, how it looks like, what its properties are. Though the idea would be just to search for this new physics in all possible ways. And I mentioned at the beginning, there are roughly speaking, there are two approaches to that. If we assume that the new physics is in one of those boxes, the direct way would be to just open all those boxes, which in this analogy would correspond to try to producing those new physics particles, new physics interactions directly at particle colliders. Or the second option would be to shake those boxes and figure out if any one of those boxes does contain something. So an analogy would be that this corresponds to looking for the virtual effects of the new particles. You don't produce them directly, but they will impact things that can be predicted in the standard model. You make precision measurements of things that you that happen in the standard model, and you compare those precision measurements with predictions, and in that way indirectly figure out if there's a new physics or not. So how does this indirect approach work? How can we discover new physics indirectly, that's potentially very heavy, with low energy precision measurements? And the sort of the classic example is nuclear beta decay. So if you look at beta decay, we have a neutron decaying into a proton, an electron, and an electron antineutrino. And this process can be described, or was described by Fermi, with a effective low energy description, just a contact interaction between a neutron decaying into a proton, an electron, and an electron antineutrino. And one can parameterize the strength of this interaction by the so-called Fermi constant. And this Fermi constant, well, we can measure it from the rate of nuclear beta decay, and that is the value that comes out. It's a constant that has a unit of 1/GeV squared. Now this, because it has units, it defines an energy scale. So we just take the inverse of the square root of the Fermi constant, and we get a mass scale, an energy scale around 250 GeV. Now, in the context of the standard model, we understand that beta decay is a consequence of the exchange of W bosons, of gauge bosons of the weak interactions. And we can relate that energy scale, or that Fermi constant, to quantities or to properties of the W boson, particularly the mass of the W boson and the coupling, this G2 here, which is the coupling strength of the W to the down quark and the up quark, and the electron and the neutrino. And we have measurements of the mass of the W, which is around 80 GeV, and that matches up roughly with that scale that we could just extract from looking at this low energy process of this nuclear beta decay process. So long before we were able to directly produce W bosons at colliders, we knew that something like the W boson had to exist just by the fact that there was a observation of nuclear beta decay. And we even were able to estimate of what the masses of those of this W boson should be in order to be consistent. Right? This estimate here would be around 250 GeV, and in fact, it came out a bit lower, around 80 GeV. And the same idea would be to search for other new physics particles in this indirect way by making precision measurements of standard model processes and inferring the existence of some heavy new physics particle. One example of how this works is to look for so-called flavor change neutral currents, which I mentioned earlier are absent in the standard model at tree level, but they actually do happen nonetheless. So even though a B quark, for example, can't go directly into a strange quark, it can take a detour. It can first become a top quark and then become a strange quark. That's a higher order loop process, so-called loop process, when there's a loop of particles that generates such a transition from a B quark to a strange quark. And what that means in the end is that those processes are very rare. They happen very rarely in the standard model because you have to take this detour from the bottom to the top back to the strange. And one can estimate the strength, sort of the coupling strength or interaction strength of such a process, where the B quark would go to a strange quark. And this example also spit out a muon antimuon pair. And one gets an expression like that. One gets a 1/16 pi squared suppression factor coming from this loop, and one gets CCAM matrix elements which are small. So this coupling is very small, this diagonal strength is very small, but it's non-zero and it's something that can be measured. So the idea is that we take processes like that, where a B quark decays to a strange quark and two muons, measure such a process very precisely calculate the standard model prediction for such a process, and compare those two things. And if they agree, well, then one would say that there can't be any additional new physics contribution, or whatever new physics contribution there is to such a process has to be very small. On the other hand, if those two things don't agree, then one could say that, oh, now I have some evidence, some hint for a new physics effect, something else that is out there that also mediates such a bottom to strange mu-mu transition. So some new physics, and one would parameterize it in terms of a new physics scale, and one would be able to, if there is an anomaly, so if there is a discrepancy between a measurement and a standard model prediction, one would be able to attribute it to some new physics, and one would be able to estimate this scale, the mass scale of that new physics. And that's, in this particular example, would be in sort of the 10 TeV range, a very high energy scale outside the direct reach of the LHC, for example. Tests like that have been performed at the LHC. There's a dedicated experiment that looks for those rare B decays at the LHC. It's called the LHCb experiment. And shown in this chart here is the data taking of that experiment up to 2018. Something like 10 to 12 B quarks have been produced at the LHCb detector so far. So they can really look for these rare decays of the B quark or the B mesons and do those tests that I described just before. Here's one example of a decay that one can look at. It's a decay of a B sub S meson into a muon antimuon pair. So at the quark level, this B meson is a bound state of a anti-B quark and a strange quark, and decays into a muon antimuon pair. So that's the level of the quark that this is transitioned from a B quark to a strange quark and two muons. And this would be an event display of such a decay. So this decay has been observed. What happens is, in a primary interaction, this B meson gets produced, it travels some distance and then decays into a mu plus mu minus pair. So in the detector, you only see these purple lines from the muons. You don't see the B sub S meson itself. You only see the secondary vertex where suddenly these muons show up. And then you can infer that there actually had to be a B sub S meson if the invariant mass of the two muons agrees with the mass of the B sub S. That's a plot that is showing this. This is not from the LHCb experiment, but from the CMS experiment, which has the latest measurement of this decay. So what is shown here is the invariant mass of the two muons, again, a histogram of events. And at the mass of the B sub S, which is around 5.3, 5.4 GeV, one sees an excess of events. This is peak here, which is due to the decay of the B sub S into mu plus mu minus. It's a very rare process. The branching ratio is around 10 to minus 9. The measured value agrees very well with the standard model prediction. This is an example where one tries to find new physics in this indirect way, but one actually didn't find any new physics. There is good agreement between the standard model prediction and the experimental result. There are related processes where those tests also can be made. There's another example of a B meson decaying into a kaon and a muon and an antimuon pair. at the quark level, it's the same thing. It's a p quark going to a strange quark and a mu and anti-muon pair. And here we have an up quark or an anti-up quark that's sort of coming along for the ride, but it doesn't really do anything. It just sits inside the B meson at the beginning and then sits inside the kaon at the end. And one can again look at the probabilities that such a decay is happening at the branching ratio of such a decay. In this case, it's what is measured is a differential branching ratio. So the branching ratio is a function of the invariant mass of the two muons that came out. And there actually one does see a discrepancy between the standard model prediction and the various measurements. So the standard model prediction here is are these gray boxes up here and over here. And all the various measurements that have been made of this decay process, they come up with branching ratios which are quite a bit lower. There's more than a 3 sigma discrepancy between the standard model prediction and those measurements. And that could be interpreted as a hint for new physics, as some new physics particle that indirectly affects those decays of B mesons and produces this discrepancy between the prediction and the measurement. And there are many other decays which show a similar trend. So there's a decay of a B sub s into phi mu or B to K star mu. They all show similar discrepancies. So this might be a hint for new physics, or it might be a result of a poorly understood hadronic effect. So the problem with those decays is that we are talking about bound states of B quarks and other light quarks, which decay again into bound states of other quarks. And there are strong interactions that are involved, strong interactions that hold together those quarks in the B mesons and in the kaon. And those effects, they might not be very well understood, and they might affect the standard model prediction. So making precision predictions here is tricky. And instead of a new physics effect, it just might be a poorly understood hadronic effect. And this is something that is a topic of hot discussion since several years now. These discrepancies are around for quite a few years now, and the question is this a new physics effect or is it not? Okay. I think I'm slowly coming to the end. What about the future of particle physics? The LHC will still run for more than a decade, until 2040 roughly, and take more than 10 times more the data than it has already taken. So it's actually quite impressive to think about the fact that we have less than 10% of the data that the LHC will produce has been produced so far. And all the results that came out from the LHC so far are done with a tiny fraction of the total data that will be available by 2040. Although many of the things that have been measured at the LHC, that have been searched for at the LHC, all those things will be done with much higher precision by 2040. But one can ask what comes after the LHC. Once the LHC has finished operations, what comes next? And there are many proposals for future colliders. So colliders that come after the LHC. And here's one chart which shows those proposals. First thing is here's again the LHC. So LHC operations, they will continue until 2040 or something like that. And yeah, they will take data, a so-called high luminosity phase of the LHC. They will have data more than 10 times than what they have now. The timescales also are a bit scary. So if you look at the timescale, it goes from now to 2090. So many decades ahead. The one problem is those big collider experiments is that they are very expensive. They are very big experiments. They require a long time to plan, to design, to build, and to run. So this planning for the future of particle physics looks very far into the future, many decades into the future. But so a bit more details what is shown here. Yeah, LHC runs until 2040 at CERN. There are two options which are discussed. One is called the FCCEE, and the other one is called CLIC. FCCEE stands for Future Circular Collider in EE, so it means an electron-positron collider mode, and CLIC stands for Compact Linear Collider. So these are, again, would be an electron-positron collider. And so both options are electron-positron. The FCCE is a circular collider. CLIC would be a linear collider. And those projects, those colliders, could start end of the 2040s, something like that. If they get approved, if they get built, end of 2040s could be the start of physics data taking, and then they would go on for a decade or two. In the case of the FCCEE, this electron-positron collider could be replaced later by a new proton-proton collider, which goes up to 100 TeV or so. So factor 7 more energy than what the LHC has so far. But that would happen very late in the 2070s or so. So that would be sort of a natural roadmap for a continuation of the collider program at CERN. That when once the LHC is done, one switches over to an electron-positron collider, which eventually will then be upgraded to a proton-proton collider of 100 TeV. The other proposals, there's a proposal in Japan to build a linear collider, the ILC, the International Linear Collider. It could start fairly early in the end of 2030s if this gets approved. So this discussion about the International Linear Collider is going on for quite some time now. And the main problem is that nobody really wants to commit to building that thing. But if there is commitment to do it, it could be done fairly quickly. And such a machine could start by the end of the 2030s. Similarly, there's also plans in China to build a new particle collider. It's called the CEPC, the Circular Electron-Positron Collider. And again, if this project is approved, it could be built fairly quickly and could run in the mid-2030s and then produce data for a decade or longer, and then eventually get upgraded also to a proton-proton machine. SPPC is a super proton-proton collider, again with a center of mass energy of around 100 TeV or so. It's unclear if any of those things will happen, but that are possible future machines to explore particle physics at higher and higher energies. What about the US? So here we have Europe, China, Japan. Oh, before I go there, here would be the footprint of the FCCEE. So these new colliders, they are really massively big. What is shown here is the LHC, the LHC ring, which is around 27 kilometers in circumference. Here is Lake Geneva. Here's Geneva, so it's a really huge collider ring, the LHC at CERN. This FCCEE, this new collider, would be around 100 kilometers in circumference. So much bigger than the LHC. It would need to go below Lake Geneva. There are geological studies trying to understand where exactly that ring should be in order to avoid the mountain ranges and in order to be able to dig that tunnel. So it would be a massive project to build something like that. But it could be done in principle, as I said, and the timelines are as shown on the previous slide. On the US side, there's quite a bit of discussion about muon colliders. Muon colliders are very interesting because they can in principle be more compact. They don't have these huge 100-kilometer tunnels. They could be much smaller. But there are issues with muon colliders, and the main problem in muon colliders is what's known as cooling. So once you produce the muons, and you produce them by starting out with a proton beam, smashing it onto a target that produces a lot of pions, the pions decay into muons, then you have to capture those muons, and you have to sort of make a muon beam out of those. The problem is these muons, they tend to go in all kinds of directions. So you first need to cool them down to basically reduce their momentum, stop them to some extent, and then continue accelerating them in one direction. And muons are not stable. They decay. They have a finite lifetime. So you have to do all of that very quickly so that you're able to collide them before they all decay away. So technologically, a muon collider is very challenging, but it seems that accelerator people think that they know how to build something like that, even though nobody has actually demonstrated to build or that one can do that and one can build a muon collider. But just from the technological point of view, it would be possible to build a muon collider, and the estimates are that it would take maybe a couple of decades or so in order to build a muon collider. And then the US, a natural site would be Fermilab. Fermilab had hosted a particle collider previously, the Tevatron, with a here's the ring of the Tevatron, which is not like I think it's around 6-kilometer ring. And then this red circle here, or this red ellipse here, that would be a possible footprint of a muon collider on Fermilab's site. So that might be a possible future collider in the US if technologically things work out. Here's a statement about the muon collider in the P5 report. So let me read that. So also, we don't know if a muon collider is ultimately feasible. The road toward it leads from current Fermilab strengths and capabilities to a series of proton beam improvements and neutrino beam facilities, each producing world-class science while performing critical R&D towards a muon collider. At the end of the path is an unparalleled global facility on US soil. This is our muon shot. So many people were very excited about that, to have this sort of clear statement by this P5 report, this clear endorsement of working towards a muon collider, to have a future particle collider in the US in a few decades from now. Okay, that's all I have. So here's again the slide that I showed at the very beginning, the various themes in particle physics that are sort of endorsed by this P5 report. On the one hand, we have this connection of particle physics with the expansion of the universe, the evolution of the universe in the context of dark matter and dark energy. We have the exploration of existing particles, trying to understand the Higgs boson, trying to understand neutrinos, and then the search for new stuff, the search for new physics, both at high energies in the context of colliders and in the context of precision measurements at lower energies. All right, that's it. Thanks a lot.
Yeah, thank you. Probably have time for one or two questions. I'm curious. I think I know the answer, but you didn't mention going after gravitons.
Oh,
So quantum gravity particles.
yes, good. Right. I think it's a very good question. I think the question of how, well, it sort of goes in the direction of how do we consistently combine particle physics with gravity. That's an sort of an entire additional open question, and I think everybody or most people would agree that gravity should be quantized in some form, and then the corresponding quanta would be the gravitons. Now, actually measuring or observing gravitons themselves, I think is very difficult. I actually don't know much about it. I mean, we do observe gravitational waves, which, however, are made from gazillion of gravitons, if that picture is right. So observing individual gravitons and observing sort of the quantized nature of gravitational waves, I think that is extremely difficult, and I don't know if there are any ways to actually do that.
Anything else in the room? If you're on Zoom, just sing out if you have a question.
I have a question.
Yes, Michael.
Can you hear? So what is sort of the current atmosphere status, et cetera, with supersymmetry, string theory, all of these things, and how that relates to particle physics? You've presented a very pragmatic, model-independent approach here.
Yes.
Like to know
Yeah.
what
So
that is.
yes. So supersymmetry, I think one of the very strong motivations for supersymmetry comes from this hierarchy problem. So one of the types of new physics that would protect the Higgs mass from fine tuning would be supersymmetry. So that would predict that there are a bunch of many new particles at the TeV scale, and one of the hopes were that the LHC would discover all those supersymmetric particles. This hasn't happened so far. I mean, there's still the chance that the LHC might discover supersymmetric particles, given that, as I said before, that they still will take much more data than they have now. So it might be that in this huge amount of data, one can find traces of supersymmetry. It's getting more and more unlikely that this will happen, but it's not completely excluded. So if one assumes that it doesn't happen, that indeed there are no supersymmetric particles in the range of the LHC, then the motivation for supersymmetry is not as big as it was before. So the heavier and heavier, I mean, you can always say that the supersymmetric particles might be just a bit heavier and outside the reach of the LHC. Well, and you can do that, but then the motivation becomes less and less compelling, because the heavier you make supersymmetric particles, the worse this Higgs fine-tuning problem gets again. So, but that's in some sense the same problem with all the proposals that try to address this Higgs fine-tuning problem, this Higgs hierarchy problem. So no matter what you do, there are some exceptions, but broadly speaking, any physics that tries to address the Higgs hierarchy problem would predict that the LHC should see some of those new physics particles. And supersymmetry is the most prominent example of that. Nothing has been found at the LHC so far. So maybe this Higgs hierarchy problem is a red herring. We don't know. It's maybe not. Maybe it's sort of that's a mild fine-tuning, and supersymmetric particles show up at slightly higher energies. We don't know. String theory, that again has to do with sort of ideas of quantum gravity and how one consistently combines gravity with particle physics. String theory typically incorporates supersymmetry to some level, and often would, but it doesn't necessarily predict that supersymmetry should be relevant at collider accessible scales. So it might be that supersymmetry shows up at very, very high scales, at the Planck scale or something like that. I think that's fine with string theory. The fact that we haven't discovered any supersymmetric particles at LHC doesn't exclude string theory, for example. It doesn't exclude the idea of supersymmetry. It just means that supersymmetric particles are not accessible at the LHC. They have to be heavier. Do they exist? We don't know.
All right, I think we should probably quit. So thank you so much. Let's thank you, speaking.
Can I ask a really quick question?
Absolutely. Maybe I'll excuse the people in the room, but go ahead, Dr.
So
Marsh.
the really quick question is, what are the current approaches to the muon cooling problem? Because just as background, in the 1960s and 70s, there was work at Stanford on this whole problem of, well, how do you make a bunch of very low energy positrons to do something with? Well, here you really got a problem to figure out if you get these collisions. Then how do you cool the? What's the approach to doing that?
Good. I'm not an expert on that, but my understanding is that, okay, well, it's called ionization cooling. So you basically you send the muon beam through some matter, and in that way, the muon beam is losing energy while it propagates through matter. Though it reduces sort of uniformly the momentum in x, y, and z direction, and then you continue accelerating in z direction, then you lead the muon beam again through the material, and then it loses energy and momentum in x, y, z direction, and you continue accelerating in z direction. So in the end, you end up with a muon beam which is mainly in z direction and has almost no momentum in x and y direction. Technologically, exactly what that means, I don't know exactly which material you need in order to do that. How this ionization cooling actually works in detail, I do not know.
So the analogy that was worked on with positrons was, if you have a ohmic conductor nearby and you get an image charge in that ohmic conductor that then gives rise to dissipation. So essentially the interaction between the image and the positron can slow it down. But in any event, I don't know if that may be an analogy. I don't know. That was something that John Mady worked on.
Okay, it might be something related. Yeah.
Thank you.
The main challenge here is that you have to do this all very fast before the muons decay all away.
Sounds like a challenge. Wolfgang, thank you so much. That was very, very informative, and I'm very happy we got you.